go, not really. Anyway, we're never going to repeat that again. All the lights in this room actually on. It seems a little like, I guess they are. Okay. Anyway, we have to, you had your turn to talk, it's my turn to talk. Just so you're aware, my office hours go until 7 after class, but we have to leave this room by 6:30 at the latest. We can't like linger because there's another student group that has this room reserved. So anyway, but I'm going to go upstairs and people can follow me and keep talking if they want. All right. So today, were there any questions lingering from last time or the time before? The time before? No? Okay, good. That's a good start. All right. So today is I'm going to start out with something that looks pretty formal and abstract, and it might be a little bit hard to follow because it doesn't seem well motivated. Some people who took GR will recognize some of the ideas, but I promise you I'm going to take the machinery I lay out in the first bit of this and I'm going to apply it to some examples that you should all be familiar with. So if you just give it some time, it will eventually touch base with things that you're more familiar with. But before I get started, I just want to finish up with a quick note based on what we talked about last time. So I'm going to very quickly construct 3 multiplication tables. I'm going to start with a group of discrete rotations that involve a rotation by nothing, the identity, and a rotation in a plane by the angle pi. Actually, I'm going to let you construct them. The next is going to be considering all even numbers, all odd numbers, and what you get with addition. So in your notes, you should be constructing these multiplication tables. You can work with your neighbor if you like. And the next one is going to be the number 1, the number -1 with multiplication. So those are your 3 groups. These are the group elements, and then the operation. The operation here is just the usual. You add the angle to compose the rotations. You know, I have no idea how many licks it takes to get to the center of a Tootsie Roll Pop. Because I just can't suck any hard candy to nothingness. Same for cough drops. You know what's awesome about having the best selfie? It's really easy to pick out and put on top. Wolfgang gets to go first. Wolfgang, what goes here? Actually here, Wolfgang. YouTube wants to see what the wolf looks like.
Wait for the camera.
Fill him in.
No, it's a scorpion.
It's scorpion.
But this is the wolf. Nice. I like it. Nice. I like it. Good. Keep going. You're doing awesome. If you need your friends to help you out, I don't know if you got any friends in this room. Bam! That's why Wolfgang is the man. Sweet. Okay, so everybody notices. Yes, give it a hand. Give it a hand. All right. So what do you notice? They're basically the same. I mean, you got different labels, but literally the structures are the same. Are these abelian or non-abelian?
They're abelian.
How can you tell they're abelian from the multiplication table?
Symmetric.
Yeah, if you actually look down the diagonal, if it's symmetric, it's an abelian group. That's one way to quickly see if it's abelian or not abelian. So these all actually represent essentially the same underlying group, which is actually the simplest non-trivial group. What's the simplest trivial group? I. It's the identity by itself. Okay? this is actually, these are all representations of what we call Z2. And Z2 is basically a group with two elements. So the identity, some element G, which is not the identity, where G squared is the identity. Okay? And you'll realize that this is sort of an abstract definition of the group, and all of these are representations of that group. Okay? Yes, Jake?
Wouldn't it be G composed G is?
Sure, sure. G composed G, you could call it, to be precise, G composed G is the identity. Yeah. Okay? This group will actually pop up a little later in our discussion, but this is just a nice representation of how a single group can have different, or a nice example of how a single group can have different representations. Again, you can construct these multiplication tables, use them to compare groups to figure out if they're the same. That only works for discrete finite groups. Later on, we'll learn how we compare continuous groups. That'll be a very, very important lesson in a couple of lectures. Okay, so for today, we're going to start with some machinery, because what we would like to do is eventually get back to the notion of we have these transformations, but we really want to talk about those transformations corresponding to symmetries, there being invariances of the Lagrangian. So let's formalize that. And one way that we could kind of just wave our hands and say, I know how I can make an invariant, is with the following very hand-wavy idea that I will formalize in a moment. If I had some object in a representation, say I'll just call it R, and if that object had some transformation rule, say it transforms to a new R by the application of some operator or matrix representation of a group element A, then if I could come up with some other thing which transforms oppositely to R, then I can imagine that if I combine that other thing with R, then the transformation of R would be canceled by the transformation of the other thing. Okay? Does that kind of make sense? So we basically want to kind of cancel off A with something that is sort of the opposite of A. Okay? So that's very hand-wavy, and now we want to formalize it. So to formalize it, what we're going to do is lean very heavily on an example that you're very familiar with, and that is the notion of a dot product. So in terms of vector representation, if I write the V as a row vector and the W as a column vector, then using the rules of matrix multiplication, what we know is that that quantity is invariant under rotations in the plane of the components of these two vectors. Okay, is that statement foreign to any of you? If you take two vectors, you make their dot product, it's a scalar, it doesn't change under rotations. We can represent that operation in terms of this matrix operation, and this is the kind of thing I want to lean on, all right? So without any further ado, if I have an object which is in a representation R of some group, so this is a representation R of G, then what I'm going to do, and so let's see, yeah, so what I mean by that is that I can take R. Let's just get it all out. All right. You know how if one person yawns, the other person yawns? I think it's happening with coffee. We've discovered a new health phenomenon here. So what I mean by an element of a representation of G is that I can transform R by the action of some element A, where A is something on G. Okay, so now what I'm going to do is I'm going to form what is called a dual representation. And for lack of a better name, I'm going to call it R twiddle. where if this is what happens to R, then what happens to R twiddle is that R twiddle goes to A inverse transpose R twiddle. All right? So what I mean by this is if I start with an element of a representation R, and I also, I kind of put it here, and then I pick an element of the dual representation R twiddle, and I put it here. If I do this to R, then I should simultaneously be doing this to R twiddle. Okay? Now this might look really strange. Well, parts of it. So A inverse is kind of what I meant when I said transforms oppositely. Okay? Inverse is pretty opposite in the way of opposites. All right? You might be wondering why this transpose. That looks weird. But remember in our dot product here, we have to transpose something. Okay? So the transposition thing we could have expected from this example here. Okay? So now let's actually take this and figure out how we make an invariant. Well, this kind of gives us some insight. To get an invariant, we took something and transposed it and then combined it with the other thing. So let's actually do that. And what I would argue to you is that R twiddle transpose R is an invariant for the following reason. If I want to transform this using A, then what I can do is say, first of all, how do I want to write this? Just make sure I didn't write this differently here. Oh yeah, it's there. Okay. Then what I can do is say, okay, well let's remember that this is secretly code for R twiddle transpose R. I did nothing but insert parentheses. Thank you, man. I appreciate it. So maybe I should say this is equal. And then what I want to do is transform with A, and now I see, well, the R twiddle is what's in here, and I know how R twiddle transforms. So I have A inverse transpose R twiddle transpose. I just transformed this R twiddle by this rule. But of course, this thing in parentheses is transposed, so I got an extra transpose there. And then I transform R. That is very busy looking, isn't it? Way busy looking. But a lot of it is kind of trivial. Because really, first of all, this is the product of two matrices. And if I'm transposing the product of two matrices, how do I break that up into two separate matrices? How do I actually distribute the transpose? I heard it. Yeah, I have to swap the order. So the transpose of the product is the product of the transposes in reverse. So I have R twiddle transpose, and then A inverse transpose transpose, A R. And now are you seeing the magic? Everybody see the magic? What's the magic? Yeah, transpose is nothing. And then I'm left with A inverse A. So lo and behold, R twiddle transpose R is exactly what I started with. Okay? Yes, Spencer, go for it. Say it. Do it. What?
Seems to suggest that the difference between R and R twiddle is a transpose. That the dual space is a transpose of them.
No.
Okay, hear me out though.
Hear me out. Okay.
Okay, so
Yeah.
that being said, what
What you said or what I said being said?
what if it's not transposed that's the difference between A and twiddles? Can there be some other operation that it's not A inverse transpose, but it's something completely different?
Well, okay, so all I'm saying to you, first of all, everything that I'm talking about is in terms of if I want to work with a matrix or linear representation of the group in question. So what we're trying to do is work with these groups in terms of things which can be represented by square matrices, column and row vectors, okay? And so that we can always employ the ideas of matrix multiplication to carry out our operations. That's the first thing. We're trying to beat this into a certain framework we're familiar with, okay? Right now, really and truthfully, I'm just saying the minimal thing that can possibly be said, which encapsulates this idea that I started out with, where I say I want to start with one thing that transforms one way, and then another thing which transforms oppositely. So hopefully you're all comfortable with the idea that if one of them uses A, the other one should use A inverse. That's kind of the minimal way to implement that. And then the transpose business is really just there so that we can use matrix multiplication in the way that we're familiar with. Because if I do this, we don't know what to do with it. Or we get a different object than what we're actually aiming for. So the transpose business is really just to give us a row vector that we can then combine with a column vector in the familiar way. Okay, it's really nothing deep. The A inverse is actually the deeper thing. Okay? Yeah, hands cross America. So go Will, Ariel, and then Rochelle.
So I might be jumping ahead on this, but is R twiddle in the dual space, or is it in the same space as R?
Our twiddle is dual.
So
first of all,
Yeah.
I haven't actually told you how to create our twiddle, and I'm going to do that next. So right now I'm just saying there's going to exist something called our twiddle which happens to transform this way. I'm going to show you what that is in a minute, and it's going to make a huge connection to GR and everything you know and love about GR, or special relativity for that matter. Ariel.
So when you say it's a dual representation, does that mean it's a dual representation of the original group G? And so is A inverse an element of G, or is A inverse transpose also an element of G? I guess inverse has to be, but
A inverse has to be, and A inverse transpose. Wow, if I have an element in a matrix representation of a group, is the transpose of that always also in the group? And I'm probably able to convince myself that it is, but it's not intuitively obvious. I could say it's an element of the dual representation of the group. So we have a representation of the group and a dual representation of the group, and we have elements of the group. No. What I'm saying is crap. I think. Yeah, I don't want to get too hung up on these, because when we go to actual examples, I think the familiarity of the examples are going to have you going, oh, okay, I see what he's been talking about. Okay, Rochelle, yeah.
I was wondering, like, if A is Hermitian, then do you automatically get that R is in Parity? Because you take because then R would be equal to R tilde, they do the same thing.
If A is so right now everything's right now I haven't said anything about complex, but so I'm going to make connections to Hermitian adjoints in just a few minutes, and there is a certain sense, so I will be able to say what you're trying to get at very concretely in my very first example. Okay? You do it?
I was waiting for a still.
You wasted time in my class waving at Chuck. Okay, and by the way, just because it got brought up, and eventually we will encounter it, if R is a complex matrix representation, okay, so if the elements of the group are complex, represented by complex matrices. Of course, if the group is represented by complex matrices, then the vectors they act on should be allowed to be complex, because even if you start with a real one, you're going to make it complex when you act with a complex matrix. If your representation happens to be complex, then your dual representation is complex, and the quantity you would form is the Hermitian conjugate of the dual, which would include transpose and complex conjugation. Okay, but still, it's going to become clearer when I look at concrete examples in just a minute how all this plays out. Okay, so now before I get into specific examples, I want to go now to this question of well, how do we actually create the R twiddles if we start with R and a group, okay? And there's a couple of different routes to get to it, but I'm just going to kind of lay out a route in terms of language that we're going to use a lot and to connect this with some familiar ideas. So, damn. So for a group G and a linear or matrix representation R, we can find an object called G, which goes by the name of the metric, such that R twiddle is built from R by the application of the metric G. I'm going to tell you how to find that metric in a minute. Okay? But the idea here now is I'm telling you the recipe for finding the R twiddles. What you start with is a representation R and a group G. So you start with these, and then from that you tease out some quantity called a metric. And then once you have this in your hot little hand, you just apply the metric to all the elements of your representation, and that's going to create the elements of the dual representation. Okay? Now, this guy right here, this metric G, it's going to be represented by a matrix. We expect that if, this is a vector, column vector, row vector, then this is going to be a vector, column vector, row vector, whatever. Then the only way this is going to make sense is if this is some kind of square matrix of the same dimension. And this is always going to be represented by a symmetric matrix. It is not a symmetric matrix, but it can always be represented by a symmetric matrix. And that distinction is important because there are people who teach that a second-rank tensor is a matrix. They are categorically wrong. The correct response is that a second-rank tensor can be represented by a matrix. Okay? So I'm saying that thing, which will end up being a second-rank tensor for the case of rotations, can be represented by a symmetric matrix. And the only thing you have to remember is it's symmetric, and we'll use that in a minute. Okay, so here we go. What I want to do is discover what the hell that thing G is. And so let's... Yeah, I love it! Damn! Son! The thing is, talking is exactly what makes it bad. Okay, so there is our invariant, R twiddle transpose R. And then what I want to do is remember, hey, wait a minute, R twiddle is built by acting on R with G. So let me secretly call this GR transpose R. I know I said GR, you're like, there's general relativity! That's not general relativity! Oh, you know what I need? I need a card loaded so that I can ask a question. Oh, I already asked one. But he's just so awesome. I think I'm going to hang on to him. Okay, where was I? I was saying something really... Oh, here we go. Okay, now, Wolfgang. What do I have to do to distribute that transpose? I want to distribute the transpose. I love this. It's like Rochelle was doing it, Jake was doing it. Everybody do the transpose dance. Spin the camera around. Let's do that. Okay, everybody do the transpose dance. Oh, it's like locked. Here we go. Oh man, I got so excited and then I broke. Yes, the transpose dance. Do the transpose dance, everybody. Everybody's doing the transpose dance. You are all going to be famous. Yes. Okay. All right. Is that actually what were we doing? I have no idea what the hell we were doing, but we did it. So transpose dance. All right. Now I'm going to pick another name. Connor Pierce. Where are you, Connor? Connor, hey man. Hey, G is symmetric. What can I say about G transpose?
It's equal to G.
Damn! You are on my Donkey Kong. It's crazy. You guys still have Donkey Kong? You better. I'd be so mad. All right. Anyway. Okay. Just making sure you guys are awake. So there we go. I transpose G. I get G back. Shh. Shh. What the hell was I doing? What? Oh, yeah. Okay. So now I want to transform this. Okay. So let's transform R. Let's transform R. Oh my God, we are getting so much mileage out of the transpose dance. This is awesome. So I get to transpose that guy. All right. But what do I want that to be equal to? Sorry. If it's invariant. So this is where I did the transformation. So I want what I get after the transformation to be equal to what I started with. I mean, this is the same thing. I want it to be equal to this. So stare at that expression very intently. And Jacob, Brandon, where are you? Jacob, tell me what I need to have be true so that this is equal to this.
You need the middle stuff to be 1.
Exact. No. No. But close. Yeah, good. So I need A transpose GA to be equal to G. Okay? Everybody see that? It's just saying this guy has to be all that crap. Now that's one of those like lines of, you know, we're doing a dance and there's stuff and we get this result, but here's the meat of the result, okay? If I give you a group G, that means I'm giving you all the A's. You know what the A's are. Like I say, you know, G is the set of rotations in 3 dimensions. Well, you know what all the rotation matrices look like. So what you can do is you can say, I want to find some matrix G such that if I pick any rotation and its transpose and act on it like this, I get back the same matrix. So you can use the transformations A to figure out what G needs to be. So that's how I'm saying you can figure out G, starting from this. Okay? So that's one way that you can work this. There's a reverse approach, which is actually what we more typically use. And that is, we could start by giving you G, giving you a metric, giving you a representation, and then from that, you can reverse engineer what the A's are for the group. And that's actually what I'm about to do in a couple of examples. But you can go either way. You could start with G and R and then figure out little g, or you could start with R and little g and go back to figure out the elements of the group. Everybody on board? Okay, so in terms of an example, let's look at one which is pretty familiar to everybody. So let us consider just ordinary vectors in 3D. So elements of my representation are going to just be given by column vectors, v1, v2, v3. And now I'm going to not give you the group, but I'm going to give you the metric. Okay? And the metric is going to be, and rarely if ever will I fill in all the zeros. Anybody recognize that metric? It's the identity. That metric is so trivial you'd probably never bother to write it down. Okay? In fact, last time we talked, when I said you've been working with these ideas all along, it's just they've never been named. You have actually been working with this machinery for a long time, ever since you first learned vectors. It's just, in that case, everything was so trivial that you never really had to name it. Today we're going to name it. We're going to start with a trivial case, but then we're going to look at examples where it's completely non-trivial. Okay? So now let's see how this works. If I want a dual vector, I just act on the vector with the metric, and then we can explicitly see what that looks like, right? If I want a dual vector, then I act on that with the metric, and so the components of the dual vector would just be, holy crap, exactly the same as the components of the original vector. So unfortunately, this example that I'm working with is so trivial that the dual vectors look identical to the original vectors. So Rochelle, this is where I was saying we would see this in an example where the dual and the original representation, they actually look identical. That's not normally the case, all right? But in this example, it is, okay? And then, of course, we know that if I take a dual and I transpose it and then I act with an element of the original representation, well, that's just what we talked about earlier. I transpose this and then multiply it onto that. This gives me an invariant. Another way to write this is V transpose GV. Okay, because again, the dual is just GV. That all gets transposed, so I flip it, and then I transpose the G, which is symmetric, so this gives me back G. Okay? And then what I could argue is that this is invariant under any A such that A transpose G A equals G. That's the condition we talked about. Okay? But here you'll notice that G is so trivial that I really could just write it as the identity. And in fact, on the left-hand side, I can really just omit it. I don't even need it. The right-hand side, I need something. So the identity is a perfectly suitable thing for the right-hand side. But so it's like if I have the equation that A times B equals 1, I could write this as A times 1 times B equals 1. Or I could just omit the 1 here, but I need to keep something on the right-hand side. Okay? Anybody recognize that condition? That is the orthogonality condition. That says if you're working with sets of matrices A, square matrices, if A transpose A is the identity, then those matrices are orthogonal. So if we're working in 3 dimensions, this defines the group of transformations O3.
Alex.
Yeah.
So we only have one matrix here, though.
One
A and a transpose. But are we saying? I guess I'm confused by what we mean by orthogonality. Is A orthogonal itself, or with this?
Right. If I take, so this is a whole set of there's a whole bunch of matrices here.
Okay.
If I pick one of them and I combine it with its transpose, then they combine to give me the identity. So there's a bunch of these matrices.
And that defines the orthogonal group.
Yes.
Okay.
This condition defines the orthogonal group.
Are they orthogonal with each other, like Will said, or are they somehow forming their orthogonal to their own transpose?
So I think what you're trying to do is bring in a notion of orthogonal for vectors and so forth.
Yeah, like functions and stuff.
Like, what does it mean for 2 matrices to be orthogonal?
Yeah, that's basically my question.
So I think you guys know what it means for a column vector to be orthogonal to another column vector because you have a notion of what an inner product is between 2 column vectors, which is secretly this machinery. But what does it mean for a matrix to be orthogonal to another matrix? Like, what does that mean? And what I'm telling you is, it means this. This is orthogonal. This is the definition of orthogonal for matrices.
But is it A orthogonal to A transpose, or is it like all of the different A's are orthogonal to each other?
No. Sorry. I get what you're saying. So this condition is saying that, okay, so that, I guess I guess there's a very big disconnect between this and vectors, because we normally don't say a vector is orthogonal to itself,
Right.
okay, unless it happens to be a null vector. And then it has that weird property, but we're not going to do null right now. So the orthogonality condition is with a matrix with respect to itself,
Okay, sure.
if you will, although that doesn't translate to the language of vectors in a way that we're familiar with.
Isn't saying a matrix is orthogonal just saying that the columns of the matrix are orthonormal to each other? Isn't that what the condition is?
Not necessarily.
No. I would not think so, but we could look at some, we're going to look at explicit examples of this in just a minute. But I would not think so. I could be wrong.
I think that it is. I think when the columns are orthogonal, then you can orthogonally diagonalize the matrix.
I think it might be the difference between an orthogonal matrix and like an orthogonal transform. Or orthogonal is
Yeah.
slightly different
Yeah.
in this context. That's what I'm thinking of.
In order to get the identity out, yeah, they would need, the first row would need to be orthogonal to the first column.
Oh, yeah, actually, so maybe we can parse this out. So you're saying I take the first, so each row is orthogonal to each column? Is that what you said?
Oh, yeah. That makes sense.
Each column is orthogonal to the other.
Yeah, actually, no, yes, okay, I agree with what you're saying. I don't, okay, here we go. Hey, here, let's just do it, screw it. If we're late, we're late. If we're late, we're late. You know, you guys want to know. And knowing is half the battle, so says G.I. Joe. Okay, for a 2x2 matrix, ABCD, there's ABCD transpose times ABCD. We want that to be equal to the identity. So if I say that the one here comes from this guy combined with this guy, right? Then I'm saying that I want the column to be parallel to itself, but then orthogonal to the second column. And then likewise, and then down here I'm saying the same thing. Yeah. Okay, yeah, I agree with you. Everything born from a concrete experiment. Okay, so what set of transformations is this? Secretly, if we were going to give it a name, if you're going to name it, if you're going to own it, what would you call this set of transformations in a more familiar, like if you were trying to teach somebody who'd never seen all this hoity-toity mathy stuff? What set of transformations is this? And don't say O3. It is O3, but like physically, what set of transformations is this?
Rotations.
In? Rotations in R3. Okay, that is exactly wrong. So let's see why. I wanted you to say that so that I could say no. Here we go. Okay, so no, and this is I'm not being mean. So this is a very instructive thing. This is where we get to revisit a lot of the definitions that we talked about last time. Okay, so I love it so much. So the A's. So this is so far what we've got. So what I want you to do is, and I'm going to call these things, I'm going to call the elements A's capital R's because we usually use that for a rotation matrix. Okay, so let me write an actual rotation matrix. So this notation is just a rotation around the x-axis by an angle theta. Okay, just to give it a name. And we know what that looks like. And if you take that matrix and you transpose it and then act back on the original matrix, you will sure enough find that it gives you the identity. Okay? But we can also take a very similar matrix, which I'm going to call not R but R prime, and that's going to be given by oh, sorry, yes, yes, yes. Okay, if it's too busy for you, the only difference is that everything on the diagonal here I multiply by a minus sign. It's the only difference between these two things, okay? If you take that matrix and you transpose it and multiply it by itself, you will find, lo and behold, that it gives you the identity. Okay? So both of these are on that set O3 because they both satisfy the defining condition for orthogonality. But what I want to argue is that this is a rotation and this is not. Okay? So let's see if we can parse out why this is not a rotation. Let's start with the idea that this is a rotation. Like if you look at this on a vector and write the components and draw pictures, you'll see, oh yeah, that's what a rotation does. Okay, so the very first thing to note is that for this guy, if you take the determinant of it, what do you think you get? Anybody see that? What's the determinant? Plus 1. Yeah, it's 1 times the determinant of this. Hey, we all know that trig identity. What about the determinant of the second one? It's negative 1. Okay? So they both satisfy this condition. So they're both in O3, but one of them has a positive determinant and one of them has a negative determinant. So that gives us some insight. Something is a little bit different. So now what we're going to do is we're going to define a group called SO3, where SO3 are the elements of O3 with the determinant equal to plus 1. So the O here is orthogonal, it's the same as the O over there, but the S means special orthogonal. Special because we're only picking those elements that have determinant plus 1. Okay? Okay, so now is when we get to do some fun stuff with what we kind of talked about last time. And that is, I have a group. What I want to do now is very quickly show that this thing is a subgroup. How do we prove that something is a subgroup? Yeah, it's got to be a group. Okay? It's a subset, obviously, because we're saying take the elements of this, so you're picking a subset. You're picking elements from the original set. You're just picking ones that have a certain criterion. But just because you pick a set of a group doesn't mean that it's a group. So let's demonstrate that SO3 actually forms a group. So we know the criterion. We have closure. We have identity. We have the presence of an inverse. And we have associativity. Okay, so we'll just run through these very quickly. So first of all, do we have closure? Okay, that's it?
Yes.
Okay, so what's tricky, so it might not be obvious, but if I take two things which satisfy the orthogonality condition and I combine them, their combination also satisfies the orthogonality condition. And you can actually work that out literally by saying, you know, AB transpose is B transpose AB. But if A and B separately satisfy the orthogonality condition, then this is the identity sitting between this, which is the identity. So bam. Okay. The interesting part, though, is this. If I take two of these matrices such that the determinant is plus 1, am I guaranteed that their product still has a determinant of plus 1?
Yes.
And, okay. So if I take an A and a B on SO3, and I consider the determinant of their product AB, well, what lovely property about determinants do we know when we have a product of matrices? It's the product of the determinants. So this is the determinant of A times the determinant of B. This, of course, is plus 1, so the determinant of the element AB is also plus 1. Okay? The identity is this thing. And hey, you know what? That has determinant plus 1. So it is on SO3. So we've got the element on this we've got the identity element on this subset. We've got closure on this subset. What about what about the inverse? Well, we know R transpose R is the identity. And so what that's telling us is that the inverse of R is just it's just R transpose. So R inverse is equal to R transpose. But then we can ask, well, wait a minute, is the determinant of R inverse equal to plus 1? Because if we discovered that R inverse had a determinant minus 1, then the inverses would not be contained in the set. But the group has to have, for every element, an inverse element. Okay? So can we argue that the determinant of R inverse is plus 1?
Is the determinant of the transpose the same as the determinant of the original?
Well, we don't have to guess it, we can prove it. Okay, so we know this because this is just the identity. Okay, but this is det R transpose det R. We've already said that's plus 1, so this is plus 1, but R transpose is R inverse. Okay? Everybody follow? Sure. I know I'm going a little bit quick. I'm going to do a couple of these examples. Lastly, the good news about associativity is since we're working with matrices, this is always guaranteed. No donkeys, no horses, no mules here. We're all golden and golden. We love our donkeys. Okay? Well, we love our donkeys. We don't love our donkeys. Not all of us. Okay, anyway. Everybody's going to want to come to Colorado School of Mines after this. All right. So now, what I want to do, okay, so a quick review. We started with a set of things which formed this group O3. But I said, hey, you know what? That's not actually the rotations. The rotations are a smaller set. The rotations are actually the set of elements of O3 that also satisfy this condition. Okay? And then we just demonstrated that that definition forms a group. Okay, so we're safe on the group front. So now let's actually explore what we got rid of. So if you stare at this for a moment, you might realize that to create an object like this, we could imagine acting with an object basically like this. Okay, basically minus the identity. Now, is that an SO3, an element of SO3? Why not?
Its determinant is negative.
Yeah, its determinant is minus 1. Okay? But here's the cool thing. If I start with any matrix of this form, I can get all of the matrices of this form, or if I take the set of matrices of this form, I can create all of the ones that I'm throwing away by acting once with this. Okay? So this special operation carries me between the set of stuff I'm keeping and the set of stuff I'm throwing away. Now, what does this operation do to the coordinates? It flips all the coordinates. So if I have x, y, and z, then this switches the direction of all three coordinates. That's just what minus does to the coordinates. Okay? That is what we call a parity transformation. It's a parity transformation on all three coordinates. You could do everything that I'm talking about instead with this matrix. Just switching one of the axes. okay? You can use either one. Either definition will work just fine, okay? Now, notice what happens. If you start with a matrix that has a determinant of +1, and you act with this thing or minus the identity, they both have the same effect, you're basically switching the sign of the determinant. Because you start with something with determinant +1, you multiply it by something with determinant -1, the product has a determinant -1. Okay? Now, one could pose this interesting question. The stuff that I'm throwing away, so do elements of O3 with determinant -1 form a group? Do those form a group? No. How can you argue that?
Multiply two of them together and they determine one.
Exactly. That's one way to do it. If I start with two matrices that have a determinant -1 and I multiply them together, their product has a determinant +1, which is violating which of the defining characteristics of a group? Closure. What else are you missing? The identity. That's probably the easiest way to see it. Okay? Okay. So now let's ask an interesting question. If we were to oh, wait, can I do it? Yeah, I can do it. Oh, sweet, this is awesome. So now I'm going to do that cool thing that I do, and you go, oh man, you're really gonna do that? Okay, so if we instead look at 2D, with that, I gotta get an eraser for this, this is gonna be sweet. With that, the defining condition is still the same. If I take this thing, and I now just keep those things, and I take this thing, I'm so excited I gotta be careful in what I'm trying to do. Okay, there we go. Yeah, that's awesome. That's so awesome. Okay. Then, oh, wait a minute. Oh, wait a minute, what happened? What's the determinant of that? Yeah, the determinant of that's +1.
It's the minus sign.
Shit. Okay, wait, hold on. Wait. So these things I get from these things just by acting with minus the identity, right?
Yeah, but not the identity.
Exactly. In 2 dimensions, this operation is actually a rotation. In 2 dimensions, if I start with xy and I go to xy, that's a rotation. In 3 dimensions, it's not. You can't take this and rotate it to form this. These are genuinely different things. They're discretely related. Okay? But in 2 dimensions, you can rotate to get here. You can still define a parity in 2 dimensions, it's just in 2 dimensions you have to use that. Okay? Because if I just reflect the x-axis, then that is genuinely different. Okay, so what we notice is there's some dimensionality sensitivity when you start talking about these things. Okay. Leave me alone. Yeah, okay, good. So are there any questions about the example of SO3, which, you know, rotations, or SO2 for that matter, rotations in 3 dimensions, rotations in 2 dimensions? Yes?
Is the parity operator, is that negatives on all the diagonals or just the...
Well, what I'm saying to you is the following. If you want a dimension-independent version of parity, then I would just reflect a single axis, because this works in any number of dimensions. In an odd number of dimensions, you can equivalently reflect all of the axes.
But in
So here's a better way to say it. Parity is a reflection of an odd number of axes. Bam. Because anytime you reflect an even number of axes, that operation is equivalent to a rotation.
So in R2, the parity operator wouldn't be the negative identity though.
Correct.
Okay.
It would be minus 1, 1, which is not negative the identity. That's why I had erased this. And then wrote it back up. Yeah. Sorry.
No, we're good, thank you.
Okay. I say that because in 3 spatial dimensions, we'll later define parity to be minus the identity. But I just want to be careful when I do that because that only works in 3 dimensions.
Sure.
If you're in 2 dimensions, you got to use something slightly different. All right, so everything that I've said here we could carry over to a complex group. So matrices with some imaginary elements. And in that case, I'll just state the result. If I, good lordy, if I look at a 2D representation with vectors that have components v1 and v2, where complex vectors in 2D with components v1 and v2, where v1 is a complex number, so it has a real and imaginary part, v2 is a complex number. I'm going to use the same metric, okay? Then if you toy around with our definition of the invariant, where now remember that you would use Hermitian conjugate, you would transpose and complex conjugate, then what you would find is that this becomes a Hermitian conjugate. Okay? And I'll leave the details of that for you to sort out. But what do we call this condition?
Orthogonality.
Say it?
Orthogonality.
No. What? Say it louder.
Unitary?
That's unitarity. So this is the unitarity condition. So when you talk about unitary transformations in quantum mechanics, when you time evolve things with the Hamiltonian, you're utilizing transformations of this type. Okay? So this represents a group, which in this case we would call U2. I know you were all wondering, how much group theory do they really know? The Joshua tree is entirely group representation theory. You guys should go back and re-listen to it. Anyway, so this condition in 2 dimensions defines the group U2, but again, we can insist on focusing on elements of U2 with determinant equal to plus 1, and these form a subgroup we call SU2. Okay. So you'll notice something interesting. You've all heard of SU2, no? Has anybody ever heard SU2? Anybody ever heard SU3? Anybody ever heard O3, SO3?
Yeah.
Okay, well these SU2, U2, SU3, they are literally defined in the exact same way as the orthogonal groups. They use the exact same metric. The only difference is that these are allowed to be complex instead of just real numbers. Otherwise, it's exactly the same. So this machinery, once you've got it set up formally, you can apply it to a buttload of different groups. And these groups are going to be incredibly important in particle physics because it turns out that all of the gauge groups underlying the forces are unitary groups, SU3, SU2, and U1.
So this does not only apply to discrete groups, or are these only discrete
Oh, I'm
groups?
sorry. These are not discrete groups. These are continuous groups. All of these groups, including the unitary groups, are continuous. And we're going to dive deeply into the mechanics of continuous groups a couple of topics from now. But sorry, everything that I'm talking about are examples of continuous groups. In fact, to kind of illustrate that, our next exercise is going to be something which is going to seem a little boring at first, but actually has a very important, it's going to lead to a very important observation in a few minutes, and that is, we're going to ask the question, if I pick one of these examples, say SON, I would like to count the number of continuous free parameters or generators of a group. Okay? This language is going to become extremely important later on in a different topic. I'm just throwing it there now, the word generator you might or might not have seen before. We will come back and talk about that in detail. But what do I mean by continuous free parameters? Well, what I mean is if I pick one of the transformations, so for example, we're going to talk about, as an example, SO3 to start with. If I just picked an arbitrary SO3 matrix, then the question is how many independent things am I allowed to adjust continuously, like dials, to create all of the other elements of SO3? Now, you might be sitting there going, well, this has got 9 elements, so you can adjust all 9 of them. But that's not quite true, right? Because if I start adjusting this element by itself, I'm going to screw up all the conditions that define this. So really, as I adjust this element, other elements have to be adjusted with it. So the question is, how many independent knobs do I have to turn? So what can I adjust? And then what other independent thing can I adjust? So to do this counting, and just working through the example might be the best way to illustrate this. So let's just start with the defining condition. So I'm going to use the most general one here. So we're going to have A, B, C, D, E, F, G, H, I. So if I take this and I transpose it, multiply it by itself, and then say I want that thing to be equal to the identity, then that is literally just an exercise in matrix multiplication. Right? And you can all do that. I trust that you can transpose this, then multiply it by the original thing and set it equal to the identity. But you know what a matrix equation means, right? It means an equation for each and every component of the matrix. Just like when we say a vector equation means an equation for each component of the vector. So literally, if this thing represents a 3 by 3 set of equations, that has to hold true for each element. And so if I actually list what all of those different results are, this will take a minute, so somebody should come up with a really funny joke. Good. Wolfgang, next time you come to class, you better come with a joke. Otherwise, I'm going to have you doing this at the board. Oh man, I'm going so fast, I'm writing it wrong. That's sending us back a notch. There we go.
All right, so,
I hear Joe Bales has got a joke.
all right, fine.
Joe Bales, you can get in front of the camera and tell a joke to the universe.
Sure, fine, whatever. So, a nun, a brunette, and a baker walk.
Whoa, Joe, done. No. We're not going there. You just said a blonde.
You don't even know where it's going.
In my okay, fine.
It's just like it couples this.
Never mind.
As long as it's clean.
You know, I think it's funny.
Alex, I'll tell you a
people don't know
knock-knock
what's going
joke.
on.
Done. Anyway, okay, back to important stuff. There we go. I just, by the way, I wasn't looking at my notes. I just did the matrix multiplication in my head and intuited the result. Anyway, so these are the 9 equations you end up getting. But careful observation reveals that, you know what? Those are the same. Moreover, and I actually have to look at my notes to see it. Those are the same. Okay? So of these, oh yeah, and same. Okay, so how many independent equations does this actually represent? 6. Okay, so this is 6 equations. Now what's important about that is the following. I have 9 numbers in this matrix, and ostensibly I could change those 9 numbers. But if I start changing those numbers, I have to make sure these 6 conditions are satisfied. So the counting actually goes that if I have 9 numbers and 6 conditions that have to be satisfied, I really only have 3 independent ways to vary that matrix while satisfying the defining conditions. Okay? Well, guess what? If you're doing rotations in 3 dimensions, you can rotate around the x-axis, you can rotate around the y-axis, and you can rotate around the z-axis. And any rotation can be built out of those 3 basic things. All right? Now, you might say to yourself, oh, wait a minute. If you start messing around with these things, are you guaranteed that you're going to keep that condition that the determinant is +1?
Wasn't that the point of this?
Well, no. So the only condition I wrote down was orthogonality. So I'm saying that, sorry, if I take an element of SO3 and I want to keep this condition satisfied, then I can only tweak 3 things. But now there's the additional question, wait a minute, what if you tweak those 3 things, but then you screw up that det R is +1?
Right.
Okay? So you got to be a little bit careful, all right? Well, that's where we make the following observation. We know that det R transpose R is +1, because R transpose R is the identity. But then we can break this up. But the determinant of the transpose is the same as the determinant of the original matrix. So this is really just det R squared. But that tells us that det R can only be plus or minus 1. Because it means the following. Watch. If I pick a matrix that satisfies this and has the determinant equal to +1, and I continuously, using things that can start at 0 and slowly move to other values, there's no way I can jump to the discrete change of getting the determinant equal to -1. So the set of elements with determinant +1 are discretely separated from the elements with -1. But we're only making continuous changes. Okay? Yes?
So when you say continuous changes, we can think of that as like theta for x.
Sure, angles. Yeah, so the rotation angles, you could use the 3 rotation angles as the parameters, the 3 parameters here. Okay, so do you see how that saves you, Matt?
Yep.
If the determinant could have actually formed a continuum of values, it would be a different story. Okay? All right. So I'm just going to... So just to give you an idea of what that counting ends up being in general, SON, I did it for SO3 because you're all familiar with rotations in 3 dimensions, but if you do it for SON, then you find that it has 1/2 n times n minus 1, 3 parameters. So, of course, SO2 has 1. SO3 has 3, and we can think of those as Rx, Ry, Rz. SO4, how many does SO4 have? Jacob's already answered the question. Will,
What?
how many does SO4 have?
6.
6. That's weird. In 4 dimensions, I have 6 rotations. But in 3 dimensions, I have 3 rotations. What's that, Flournoy? Exactly. How do I have 6 rotations in 4 dimensions?
Because the rotations are defined by the planes that you're rotating.
Boom. This is one of the things that never gets taught to you in physics, because you always work in 3 dimensions. But it is very true, and it's very important in this class. We talk about a rotation around the x-axis, but that is a very bad way to define a rotation. This should be called a rotation in the yz plane. This should be called a rotation in the zx plane, and this should be called a rotation in the xy plane. Because we rotate in a plane. We don't rotate about an axis. And the problem is exactly that in 4 dimensions, if you pick a 2-dimensional plane, there are 2 directions perpendicular to it. So if you're rotating in the xy plane in 4 dimensions, you can't call that a rotation around z. Because there's another axis w that's perpendicular to that plane. So we just need to call it what it is, a rotation in xy. And then you can see that you have the other rotations and r, y, z. Okay? Yes? Nathan?
Is SU2 isomorphic to SO4?
We're going to talk about that in due time. So we're going to talk about how you compare continuous groups and determine whether they're isomorphic, and that's going to be a very, very interesting question. So in due time on that. I don't want to jump ahead though. Okay, so so just as a really quick last contrast, because you can't, partly because it's going to be important for your homework, but also because, well, 2 comments to be made. So number 1, what if I chose SU here? Yeah?
Is the argument kind of collapsed because I can have a continuum of determinate values, at least this argument?
Yes, exactly. That's what's going to change. So if this was SU instead of SO, all right, excuse me, much of this argument is going to play out. You could write down these equations, except now everything is going to be daggers, daggers, daggers. Or actually, these are just elements, so these are complex conjugates. I've got the example written up in the notes. Okay, so all of these equations are going to be similar, except you're going to have complex conjugates in a lot of places. Okay, but where you're going to have one very important difference is this guy right here. Because this is Hermitian conjugate. And so this is going to say that det R star det R is equal to +1. Because you can still get rid of the transpose part because the determinant doesn't care. But this has a continuous family of solutions. Okay? So what happens is, in the case of SU3, so here, so let me see if I can get a really quick and dirty. So SU3 is like doubling. So very quickly, what would SO6 be? 15? 16? Shit, that's not going to work. Okay, yeah, it's not going to work. So
3 times 5 is 30, divided by 2 is 50.
Yeah, it's still not going to work. So I'm not going to take the time to write this down because it's going to take too long. But look in the notes. There's an example of doing this for a unitary group, so a complex group. And it could be that when I write down these equations, I can't identify so many of them as being the same. Okay? So, but nonetheless, at the end of the day, you write down the unitary condition that R transpose, or R Hermitian conjugate R is the identity. You write down an arbitrary complex 3x3 matrix. You write down this equation explicitly. You get a system of complex equations, which must hold for the real and imaginary part. And then you figure out how many independent constraints does that impose. And then you add another constraint. Okay? So Say it again?
Does that reduce the number of?
It reduces the number of free parameters. So in the end, when you do the unitary case, what you find is SUN has n squared minus 1 free parameters, okay? Which is a different result than SON. Okay, again, I do this explicitly in the notes. We just don't have time to write it up on the board. And now if we just look at a couple of examples, U1, which by the way is SU1, you don't really have to distinguish so much. U1 has 1 free parameter. SU2 has 3 free parameters. SU3 has 8 free parameters.
Isn't that 0? Isn't U1?
Say it again?
Well, I just used the formula there. Isn't that 0 free parameters for U1 or is it 1?
It's U1, not SU1. So you don't have to impose that det R equals plus 1 condition. So its counting is actually an exceptional case. Okay? And I'm doing all of this because there's a punchline here. Okay? There's nothing intuitive about this, right? This is just like, yeah, unitary cases, I have no idea what the F they are. Okay? However, what I will tell you is the following. This group, U1, is the group for electromagnetism. This group is the group for the weak interactions. This group is the group for the strong interactions. And for electromagnetism, we have 1 photon. We have 3 gauge bosons, and we have 8 gluons. So these particles, which you've probably heard the names of, if you've ever looked at the Standard Model in any popular book, the gluons, the weak bosons, and the photon, they mediate forces. They are going to exactly correspond to the free parameters in the groups that underlie those forces. And we'll see this play out in detail later on when we actually study the Lagrangians. Okay? So one last comment. This will just take a second because you need it for the homework. If I gave you a theory of 3, or let's say 4 component vectors, V1, V2, V3, V4, and I gave you a metric that looks like this, what group do you think I'm starting to define? SO4. Okay? It's the group of rotations in 4 dimensions. It's just the generalization of 3-dimensional rotations. Ready? What if I did this?
SO1, 3.
Exactly. What I've done is I've treated one of these coordinates differently, and to name this, we would call it SO1, 3. Or you could call it SO3, 1. It's your choice. What physically is this important for? This is special relativity. So special relativity is not rotations in 4 dimensions. It's different in that the metric that we use to form the duals is different by a minus sign in one of the spots. Okay? And then I'll just say this because some of you might be reading the book. There's a huge convention difference between GR and particle. This is a particle course. In GR, we usually put a minus here and then pluses, whereas in a lot of particle physics books, they prefer to do that. Okay? It's just a convention change. It does change a lot of formulas later on. All right? To start with, I'm going to use the GR convention, and then later on we might have to switch, just so that we can sync up with the literature. Okay? Any questions? You guys are welcome to come and talk to me here in this room for about 10 minutes, and then we're going to skid out. I will.
So the condition of the orthogonality group is that the transpose in itself gives you 1, or the identity, not the measure. Because in our example,
Yeah. So very, very good observation, Will. So remember, the condition is A transpose G, A equals G. And you can't say that this is the identity. So when you plug this in here and you start finding out what the A's are, what are they going to be?
not orthogonal?
They're going to be the Lorentz transformations and rotations. Okay? All right, we'll look at more details of that next time. Everybody, we've got, Zach has office hours posted on the website. Yes, thank you. Excellent response. Your homework is due Tuesday. I'm going to have office hours Monday night. Zach will have office hours Tuesday morning / afternoon. Shut it down. Shut it down.